You've probably written code like this 1,000 times. A simple call to read. You pass in a file descriptor, a buffer, and a size, and it just works. Data appears in your buffer, and you move on with your life. But have you ever stopped to wonder what actually happens inside that call? Because behind this one innocent line of code, there's a hidden boundary, an invisible wall that separates your program from the operating system kernel. Your program runs in user space. It cannot directly touch the disk, the network card, or any hardware. The kernel controls all of that, running in a completely separate, privileged world. And every single time your program needs to interact with the outside world, reading a file, sending a packet, allocating memory, it has to cross that boundary. So how does it cross? What actually happens at that wall? That's what we're going to explore today. The system call, the hidden gateway between your programs and the kernel. But first, why does this boundary even exist? Why can't your program just talk to the hardware directly? The answer is protection. Modern CPUs have a concept called privilege rings. Think of them as concentric circles of trust. At the very center is ring 0, the most privileged level. This is where the kernel runs. It can do anything. Execute any instruction, access any memory address, touch any hardware device. Your programs run in ring 3, the outermost, least privileged ring. Programs in ring 3 cannot execute privileged instructions. They cannot access hardware directly. They cannot read another process's memory. The CPU itself enforces these restrictions. This isn't just a software convention. It's baked into the hardware. If a ring 3 program tries to execute a privileged instruction, the CPU will immediately raise an exception and kill the process. Without this protection, a single buggy program could corrupt your entire file system, crash the network stack, or bring down every other running process. The boundary exists to keep everything safe. So how do we actually cross the boundary? It starts with the C library. When you call read in your C program, you're not calling the kernel directly. You're calling a wrapper function in glibc, the GNU C library. This wrapper does the setup work that the kernel expects. On x86-64 Linux, system calls use a specific register convention. The wrapper places the syscall number into the RAX register. For read, that number is 0. Then it loads your arguments into specific registers. The file descriptor goes into RDI. The buffer pointer goes into RSI. The byte count goes into RDX. Each system call has its own unique number. Read is 0, write is 1, open is 2, close is 3. There are about 450 of them on modern Linux. Once the registers are loaded, the wrapper executes a single, special CPU instruction, the syscall instruction. That's the moment everything changes. That instruction is the actual gateway, and it triggers a hardware event that we'll explore next. The syscall instruction is where the magic happens. When the CPU executes it, 3 things happen simultaneously in a single atomic operation. First, the CPU flips its privilege level from ring 3 to ring 0. Your process is now running in kernel mode. Second, the instruction pointer jumps to a fixed address, the kernel system call entry point. This address was configured by the kernel during boot. You can't choose where to jump. The CPU enforces that you always enter the kernel at this one specific, predetermined address. Third, the CPU saves the user's return address and flags so it knows where to come back to after the kernel is done. This is fundamentally different from a normal function call. A normal call just pushes a return address onto the stack and jumps. The syscall instruction changes the CPU's entire privilege context. It's a controlled, hardware-enforced mode switch. And that's the beauty of it. The hardware guarantees that user programs can only enter the kernel through this one narrow, audited gateway. There is no backdoor. Now we're inside the kernel. The CPU has jumped to the kernel's entry point, and the first job is figuring out what the caller actually wants. This is where the Syscall table comes in. It's conceptually simple, just an array of function pointers indexed by the syscall number. The kernel reads the value in RAX, which the C library set to 0 for our read call. It checks that the number is within the valid range. Then it looks up index 0 in the table and finds sysread, the kernel's implementation of read. Index 1 is syswrite. Index 2 is sysopen. Index 3 is sysclose. And so on for about 450 system calls on a modern Linux system. It's literally an array lookup. Table bracket 0 gives you sysread. Table bracket 1 gives you syswrite. No complex routing, no string matching, no hash maps, just a number, an array, and a function pointer. Once the kernel has the function pointer, it calls the handler, passing along the arguments from the registers. Now the real work begins. The sysread handler now has everything it needs: the file descriptor, the user's buffer address, and the byte count. But the kernel doesn't just blindly read data. It goes through several careful steps. First, it validates your arguments. Is the file descriptor actually valid? Does it refer to an open file? Is the buffer pointer a legitimate address in user space memory, not some garbage value or kernel address? Next, it checks permissions. Does this process have read access to this file? Then it consults the virtual file system, the VFS layer. This is the kernel's abstraction that lets the same read call work whether the file is on an ext4 disk, an NFS network mount, or a virtual proc file system. Now comes the actual data retrieval. The kernel checks the page cache first, a region of memory where recently accessed file data is kept. If the data is already cached, it's a cache hit. The kernel just copies the bytes to your buffer. Fast. If it's a cache miss, the kernel initiates a disk read, often using DMA, direct memory access. Your process goes to sleep until the data arrives. The handler is done. The data has been copied to your buffer. Now it's time to return. The kernel places the return value into the RAX register. For a successful read, this is the number of bytes actually read. If something went wrong, maybe the file descriptor was invalid, or you hit end of file, RAX gets a negative error code instead. Then the kernel executes the sysread instruction, the reverse of syscall. The CPU flips the privilege level back from ring 0 to ring 3. The instruction pointer jumps back to the user's code right after the original syscall instruction. You're back in user space. The glib wrapper picks up from here. It checks the value in RAX. If it's 0 or positive, that's your return value, the number of bytes read. If it's negative, glib translates it into the familiar C error pattern. It stores the positive error code in the global errno variable and returns -1. And that's the complete round trip. Your simple read call traveled from user space, through the C library, across the hardware boundary, into the kernel, did the real work, and came all the way back. Everything we've discussed isn't just theory. You can actually watch system calls happening in real time. The tool is called strace. Run strace followed by any command, and it will intercept and display every single system call that program makes. Let's try it with a simple cat command on a small file. The output is revealing. First you see execv, the syscall that launches the program itself. Then a flurry of openat and mmap calls as the dynamic linker loads shared libraries. Then the actual work: openat to open your file, read to pull in the data, write to send it to standard output, and close to clean up. Even this tiny command makes around 30 system calls. A web server handling a single request might make hundreds. Each line shows the syscall name, its arguments, and the return value. If something's going wrong, a file not found, a permission denied, a connection refused, strace shows you exactly which syscall failed and why. It's one of the most powerful debugging tools in a Linux developer's toolkit. System calls aren't free. Every boundary crossing has a real cost. A regular function call takes roughly 1 to 5 nanoseconds. It just pushes a return address and jumps. But a system call takes 200 to 1,000 nanoseconds. That's 100 to 1,000 times slower. Why so expensive? Every syscall involves saving and restoring CPU registers, flushing parts of the CPU pipeline, switching privilege levels, looking up the handler in the table, executing the handler, and then switching all the way back. That's a lot of work for the CPU. This is why good systems programming obsesses over reducing syscall count. Reading a file 4,096 bytes at a time with a single read call is vastly better than reading 1 byte at a time with 4,000 individual read calls. Same total data, but 1,000 times less overhead. It's also why memory-mapped files using mmap are so popular. Instead of calling read over and over, you map the file into your address space once. After that, accessing the data is just a memory read, no syscalls at all, until a page fault triggers one behind the scenes. The fastest system call is the one you never make, and modern kernels have some brilliant tricks to avoid them. The first is vDSO, the Virtual Dynamic Shared Object. The kernel maps a tiny piece of code directly into every process's address space. For frequently called operations like getting the current time, the kernel updates a shared memory page, and your process reads it directly, no mode switch, no boundary crossing. What used to be a full syscall now costs the same as a regular function call. The second breakthrough is errno, introduced in Linux 5.1. Instead of making individual system calls for each I/O operation, errno uses two shared ring buffers between user space and kernel space, a submission queue and a completion queue. Your program fills the submission ring with I/O requests, and the kernel fills the completion ring with results. Thousands of operations can flow through with 0 mode switches per operation. This is the future of high-performance I/O from the early days of expensive trap instructions to zero copy, zero syscall I/O. The boundary between your programs and the kernel keeps getting thinner. And now, you know exactly what happens when you cross it.